Hey everyone, welcome back to the channel. In this masterclass we are doing a complete, from the ground up deep dive into JVM architecture and class loading. By the end of this video you'll understand it well enough to use it confidently in production and explain it clearly in an interview. If that sounds good, make sure you are subscribed and let's get started. The JVM does not load classes by magic. It follows a strict, deterministic sequence: find, load, link, initialize, and every mysterious class path error you have ever seen is a violation of one step in that sequence. We are going to dissect each step so that the next time something breaks, you know exactly where in the pipeline to look. The JVM is composed of three collaborating subsystems. The ClassLoader subsystem is responsible for bringing bytecode into memory. The runtime data areas are where that bytecode, its data, and the call stack all live. The execution engine is what actually runs the instructions. Today we focus almost entirely on the ClassLoader subsystem because that is where loading failures originate. Quick pause: if this is useful so far, drop a like, subscribe for a new masterclass every week, and share it with a teammate who would find it useful. Now back to it. Bytecode enters through the ClassLoader subsystem and is placed into the runtime data areas. The method area holds class-level metadata and static fields. The heap holds object instances. The JVM stack holds per-thread call frames. Once class data is resident in the method area, the execution engine can interpret or compile it. The garbage collector is also part of the execution engine. It reclaims memory from the heap and, under certain conditions, even unloads classes from the method area. Every class you have ever written goes through these four phases before a single line of your code executes against it. Loading is purely I/O, linking is structural validation and memory preparation. Initialization is when your static blocks actually run. Unloading is rare in server applications, but critical to understand in OSGi, application servers, and any system that hot deploys code. Linking is the phase developers skip over, but it contains the most detail. Verification is the JVM's security boundary. It ensures no bytecode can corrupt memory or bypass access control. Preparation zeroes out static fields before your initializer runs, which is why a static int is guaranteed to start at 0 even without an explicit assignment. Resolution is lazy by default. A symbolic reference like com.example.payment service is not resolved to an actual memory address until the first time that reference is actually used. These two are the most confused pair in all of Java error handling. ClassNotFoundException is a checked exception thrown when you explicitly ask a class loader for a class by name and it cannot find the bytes. NoClassDefFoundError is thrown by the JVM itself during the resolution substep of linking, when a class that the compiler knew about at build time simply does not exist on the runtime class path. The canonical cause is deploying a jar without its transitive dependencies. The compiler saw the class, the JVM at runtime cannot. Class.for name is the canonical way to load a class by its fully qualified name at runtime, and it is the primary site where ClassNotFoundException surfaces. The class loader searches its delegation chain, bootstrap, platform, then application, and if none of them can locate the bytecode, it throws. This pattern is the backbone of JDBC driver registration, plugin systems, and any framework that loads user-supplied classes by name from configuration. The delegation model is the single most important rule to internalize about class loaders. When a class loader receives a load request, it does not attempt to load the class itself first, it passes the request up to its parent. Only if the parent chain returns empty-handed does the child attempt to load the class from its own source. This design prevents application code from shadowing core JDK classes, which would be a serious security vulnerability. Custom class loaders in frameworks like Tomcat deliberately break this delegation in a controlled way to achieve class isolation between deployed applications. Class loading is one of those topics where shallow knowledge causes real production incidents and deep knowledge separates senior engineers from the rest. We are going to build a precise, complete mental model, starting with why it matters, then the full pipeline, then the exact vocabulary you need to reason about it correctly. The single most important thing to internalize is that the JVM loads classes on demand, not all at once at startup. This is a deliberate design decision with cascading implications. every time a class is referenced for the first time, and not before, the JVM triggers the loading pipeline for that class. This means class loading is happening throughout the entire lifetime of your running application. These are not academic curiosities, each one maps to a class of real-world problems. The distinction between ClassNotFoundException and NoClassDefFoundError trips up even experienced developers because the names sound nearly identical but the root causes are completely different. Application server isolation, framework magic like Spring Boot dev tools hot reloading, and the risk of static initializer deadlocks all become fully explainable once you understand the class loading pipeline precisely. This is the complete pipeline every class travels through before your code can use it. Loading finds and reads the binary data and creates the class object. Linking has 3 subphases. Verification confirms the bytecode is safe, preparation allocates static fields with their default values, and resolution converts symbolic references into direct memory references. Finally, initialization executes static initializers. By the end of this section you will be able to explain every one of these phases with precision. Imprecise vocabulary is the root cause of most confusion around class loading, so let us fix that now. A class file is simply the binary artifact produced by the compiler. A class loader is a JVM object whose job is to locate binary data for a named class and hand it to the JVM. The distinction between the defining loader and the initiating loader matters because of delegation. A loader that receives a request may delegate upward rather than load the class itself, making those two roles different objects. The runtime constant pool is where symbolic references live before resolution replaces them. This distinction is subtle but critical. When class loader A delegates a request to class loader B, A is the initiating loader and B is the defining loader. The JVM uses the defining loader as part of a class's identity, so if the exact same bytecode is loaded by 2 different defining loaders, the JVM treats them as 2 completely different types. This is the foundation of application server isolation and the source of many ClassNotFoundException surprises in frameworks. Calling getClassLoader on a class object always returns its defining loader, the loader that actually supplied the binary data. Bootstrap-loaded classes like string return null because the Bootstrap class loader is implemented in native code and has no Java object representation. Calling getParent walks the delegation chain, which is how the JVM enforces the parent delegation model we will explore in the next slides. This section gets into the machinery the JVM uses before a single line of your application code runs. We will move from the binary layout of a class file, through the class loading pipeline, and into the identity rules that govern the Java type system at runtime. These concepts underpin everything from dependency isolation to ClassNotFoundException debugging. When Java compiles your source file, it produces a binary stream that must conform exactly to the Java virtual machine specification. The first 4 bytes are always 0xCAFEBABE. The JVM checks this immediately and rejects anything else. The 2 bytes that follow encode the major version number, so a class compiled with Java 21 carries major version 65. If you try to run that class on a Java 8 JVM, which only understands up to major version 52, the JVM throws unsupported class version error before it even looks at your bytecode. These are the first 8 bytes of any Java 21 class file rendered as hex. The magic number 0xCAFEBABE was chosen by James Gosling's original team partly as a nod to Silicon Valley coffee culture, and partly because it made class files trivially identifiable. The minor version is almost always 0, the major version is what you need to track when managing multi-version deployments or diagnosing version errors. After the header, the class file is organized into well-defined sections. The constant pool is the most important. It holds every symbolic reference the class ever makes, class names, method signatures, string literals, all as human-readable names rather than memory addresses. Access flags are a bit mask that tells the JVM whether this is a public class, an interface, or an abstract type. The code attribute inside each method descriptor is where the actual bytecode instructions live. The constant pool will be central when we discuss the resolution phase of linking. The constant pool in the class file is a static, on-disk structure containing symbolic names. When the JVM loads the class, it creates a corresponding runtime constant pool in heap memory. Initially, that pool holds the same symbolic references, strings like COM example payment service. During the resolution phase, those symbolic references are replaced by direct references, actual memory pointers and method table indices the JVM can act on without any further lookup. This two-stage design is what lets Java resolve class dependencies dynamically at runtime rather than statically at compile time. A class loader is not a JVM built-in, it is an ordinary Java object you can subclass and customize. Its contract is simple: given a fully qualified class name, produce the bytes that represent it, then hand those bytes to the JVM to define a class object. The class loader is deliberately agnostic about where the bytes come from. Application servers use this to load different versions of the same library in isolation. Frameworks use it to generate proxy classes entirely in memory at runtime. This is the rule that trips up experienced developers. If ClassLoader A and ClassLoader B each load a copy of com.example.userService from different jars, the JVM sees two completely unrelated types even though the names are identical. An object whose class was defined by ClassLoader A fails a cast to the user-service type defined by ClassLoader B, producing the famously disorienting message user-service cannot be cast to user-service. Once you internalize this rule, that error message becomes immediately diagnosable as a class loader boundary violation. When a class load is triggered, the class loader that receives the initial load class call is the initiating class loader. Because class loaders typically delegate to a parent before trying themselves, the class may ultimately be defined by a completely different class loader higher up the chain, that is the defining class loader. The JVM permanently associates a class object with its defining class loader, not its initiating one. This distinction becomes critical when we walk through the parent delegation model in the next concept. Concept 5, the method area and metaspace narrator. When the JVM loads a class, the class metadata has to live somewhere in memory. Where? In modern Java, Java 8 and beyond, this location is called the metaspace. Passive uses what does not trigger initialization narrator. Now let's talk about passive uses, situations that look like they might trigger initialization but don't. This is where a lot of confusion lies. 3 code examples appear. Narrator, passive use 1, compile time constants. Let's recap the key takeaways from this masterclass. If this helped you, hit the like button, subscribe for a new deep dive masterclass every week, and forward this to a teammate who would find it useful. Drop your questions in the comments, I read every one. See you in the next one.